In the previous two videos, we talked about control volume and control volume analysis. We looked at conservation of mass principle for a control volume. We looked at the conservation of energy principle for a control volume. And now in this video, we're going to continue that discussion. And now we are going to apply those principles onto different devices that are usually of interest when we talk about engineering devices, or when we talk about devices that function on the basis of thermodynamic laws. So we're going to be talking about different types of devices like nozzles, turbines, compressors, and we're going to see how those devices are based on these conservation principles for control volumes, because not only energy is being exchanged between the system and the surroundings, but mass is also being exchanged between the system and the surroundings. So just to review the equations that we looked at previously, so we looked at the steady state forms of the mass and energy rate balances, and this is what we will be applying in the discussion in this video. We're going to be looking at the steady state equations, and the first equation was obviously the conservation of mass for a control volume. So the incoming mass is equal to the outgoing mass, or the incoming mass flow rate is equal to the outgoing mass flow rate. And then we also looked at the energy principle in terms of the steady state equation. So the left hand side was reduced to zero, which was the change in the energy of the control volume with respect to time. So that goes out of the window, and then we're left with the rate of energy transfers in terms of heat content, in terms of work transfer, and in terms of the energy that is being carried by the incoming fluid or the stream, and the energy that is being carried out by the outgoing fluid. So these are the two equations that we looked at, and then we also basically just wrote this equation down in terms of the rate of energy into the system and in terms of rate of energy out of the system. And then we applied these same equations onto a special case, which was a one inlet, one exit control volume. So for example, it could be any kind of system that would have only one inlet and only one exit. And obviously the sizes of these inlets and outlets can vary, and the control volume is specified by these dotted lines in here. And because we are only looking at a one inlet, one exit special case at a steady state, so what that means is that the incoming mass flow rate is equal to, because we are looking at all the incoming mass flow rates, so mi dot should be equal to, so all the incoming mass flow rates at the inlets, they would have to be combined, should be equal to all the outgoing mass flow rates. And because we've got only one inlet and one outlet, that reduces the equation to m dot 1 equals m dot 2. And then the energy principle is basically reduced as well, because now we've got m dot 1 equal to m dot 2, and this is equal to m dot, basically. So we don't need to calculate m dot 1 separately and m dot 2 separately, because we know that they're equal to each other. So we are left with this equation here, and in terms of dividing the entire equation by mass flow rate, we could also write this equation like this. So now we're just going to move on to, now that we've reviewed what we looked at previously in the previous video, we can just go on and apply these principles onto, first of all, devices that are called nozzles and diffusers. And for a nozzle, what a nozzle is basically a flow passage where the area is decreasing. So this is basically a nozzle. The area decreases from section 1 to section 2, and as the area is decreasing, the velocity is increasing in the direction of the flow, right? And the diffuser is kind of the opposite of this. So the area is increasing from section 1 to section 2, and the velocity is decreasing in the direction of the flow. And both of these devices work on the basis of the same principles, and obviously these devices are devices that you've usually seen in and around you. So basically, like a garden hose that is based on the application of a nozzle. Then you've got wind tunnel facilities. They are a combination of nozzles and diffusers. Then your air conditioning systems, they've got passages that would be converging, and then passages that would be diverging. So basically operating on the principles of nozzles and diffusers. So for nozzles and diffusers, because they are controlled volumes, so mass can go into the system, mass can leave the system. The same goes for the diffusers as well. So if we were to write down the equation based on the conservation of mass principle, and because we are only looking at steady state, remember, so this term goes out, and we're left with m dot 1 equal to m dot 2 basically. And then if we look at the conservation of energy principle, then again the left hand side goes to 0, and on the right hand side over here, because so if we talk about this term here, work is only taking place over here because of the flow work. That means that work is only taking place because of the fluid that is moving in. So the work that is associated with the mass flow, we've talked about this in the previous video. Go and check it out if you don't understand this concept here. But we talked about flow work, and flow work is applicable at the locations where the mass is entering into the system and mass is leaving the system, right? So that means this term over here, this is composed of U1 plus P1 V1, which is the specific volume. So flow work is basically this term in here. So in terms of work, this is all the work that is being done. This term over here, this is going to drop out because there's no rotating shafts in here, no other kinds of work that are being done. So this term is going to drop out. And what we're going to be left with is this term in here, obviously m dot 1, that is being divided and multiplied by this term over here that includes the flow work, and then the kinetic energy and the potential energy changes. But again, the potential energy changes aren't really taking place because the system is not being elevated or anything like that. So these terms go out as well. Kinetic energy changes, again, those could take place or those could be dropped out if they're small enough. So that is something that you have to look at on a case-by-case basis. And in some cases, these terms here, the kinetic energy terms, they can be dropped out. So you have to be careful with these, depending on the problem that you're looking at, depending on the system you're looking at. So once these terms drop out, what you're essentially left with is this equation, because m dot 1 is equal to m dot 2. So that gets canceled out, and what you're left with is this equation. So this equation is important because if, let's say, you've got enthalpy given to you at state 1 or subsection 1, then you could find out the enthalpy at section 2, or vice versa. And then this is obviously your kinetic energy changes over here. If these are small enough, then you can drop this entire term out. But again, you have to look at this on a case-by-case basis. In some problems, you may not be able to drop this term. The check for that would be if velocities are given to you, then obviously include these terms. Otherwise, just go ahead and exclude these terms if you want. So these are this is how you work out basically uh, nozzles and how they're based in control volumes. Why is it a control volume? Because mass is also being exchanged between the system and the surroundings, besides just energy. So if you want to practice this, I would recommend that you go to Shapiro's book and look at example 4.3, which is about calculating the exit area over here of a steam nozzle. So you will have a good idea once you apply these equations onto um, an example problem. The next system that we're going to look at, or the device that we're going to look at, is a turbine. And a turbine is an extremely important device because that's the device that develops the work, right? So uh, whatever the case may be, whether it's a gas or a liquid that is passing through the set of blades, for example, that is being shown here, these set of blades are then attached to this shaft in here, and once these blades start rotating, the shaft starts rotating as well, and then this shaft is attached to, let's say, systems that convert this mechanical form of the energy into the electrical form of energy, and that's how electricity is produced as well. So shaft work is being produced here, and these turbines are being used everywhere around you in vapor power plants and gas power plants, aircraft engines as well. So whether it's a hydraulic turbine, which is being used in the dam, or whether it's a wind turbine that is being used in a wind turbine facility, turbines are really important applications and devices. So we have to obviously analyze how these work. And again, we're looking at turbines operating at steady state. So m dot 1 is equal to m dot 2. And other than this, when we look at the energy equation, uh, some terms are going to be dropping out of here because, again, the elevation changes don't really take place. Other than this, the kinetic energy changes could be considered small enough that they could be neglected. So it's not that they don't exist, it's just that they're negligible enough compared to all the other variables given in here that you can neglect these terms. So the only terms now that you're left with are the heat content rates and the work transfer rate and enthalpies. So usually what you do is, instead of looking at what is happening within the system in terms of the rotating blades and in terms of the stationary blades, you just take it as a black box, and this is how you represent it. So in any problem, once you see this symbol, this means that you're looking at a turbine, and obviously it's connected to a shaft over here, and work is being produced by the rotation of this shaft. So obviously, now that we have a rotating shaft, which is a part of our system, that means that this term is important now and we cannot ignore it. Other than that, heat content, again, this is something that is usually a part of turbines, so you have to include this term in here. And then obviously enthalpy changes are taking place for a turbine, so you have to include these terms in here as well. So essentially, your equation is reduced to this equation. Again, you have to be careful with this term. So maybe don't neglect it straight away. Keep it a part of the equation over here. But again, depending on the problem, if you've got velocities given to you and you see that the change in velocity is, because it's a square of the velocity now, so the change could be greater. So if this change is not negligible enough, then include this term, keep it in here. Otherwise, if this change is small enough, you don't have to take that into account, but then you would know if you have to take it into account or not, depending on the problem that you're solving. Um, so yeah, this is how you analyze turbines. Again, if you want to practice this, go ahead and look at problem or example 4.4 in chapter 4 in Shapiro's book. I'm talking about the 5th edition, Fundamentals of Engineering Thermodynamics by Moran and Shapiro. So just take a look at this example, solve it yourself so you have a good idea about how you can um, work with this kind of problem. Also, you should be able to look at how the TV diagram for this would look like. So maybe practice with that too. Look at how the PV diagram is going to be generated as well. So look at TV diagram for this problem and also look at the PV diagram for this problem. So basically work out everything and then at the end generate these two diagrams. So you have an idea of what the process for a turbine is going to look like on your PV curve or on your TV curve. So the next system that we're going to look at, and just this is just how you're going to be looking at this equation if there was no heat transfer rate involved. But let's not look at this equation. Let's just stick to this one because if you look at this equation, then you could go ahead and neglect it. But if you start by this equation, then obviously you could be missing out vital information if, let's say, this term was given to you or if this term wasn't negligible enough. So just work with this equation and not this one straight up. This is a simplification. This is a simplified case of this equation. So the next system that we're going to look at or systems that we're going to look at are compressors and pumps. They operate on the basis of the same equations, so that's why we lump them in together. And compressors are basically devices where now work is being done on the gas. So previously we looked at turbines where the work was being generated, you could say, and now work is being input into the system. So this is what a compressor would look like. And the basic difference between a compressor and a pump, although both of these terms are used interchangeably, so compressors or pumps, doesn't really matter. But if you had to go into the technicality of it, so pumps are also supplied work, and they're used to change the state of the fluid. So state of the liquid that is passing through, that would be changed, let's say, into a different state. It could be a mixture that is passing through the pump and then you're changing it completely into a liquid. So that is the technical difference between a compressor and a pump. And then there's obviously different compressor types, and you've got reciprocating compressors, and you've got other centrifugal compressors and other types of compressors. But we're not going to look at the types of compressors here. Again, we're going to treat it as a black box, and we're just going to consider a compressor in terms of this symbol. So previously we looked at a turbine. The symbol for a compressor is the opposite of it. Wherever you see this symbol in a problem, okay, let me just get it right. Wherever you see this symbol in a problem, this would represent a compressor. And obviously, again, with the compressor as well, you've got a rotating shaft in here. So that means work done is going to be an important component of the equation. First of all, though, because we're looking at a steady state operation, so and because we've only got one inlet and one outlet system here, so that's why m dot 1 is equal to m dot 2. And then the energy equation, just like we saw for the turbines, we're gonna have the same equation for compressors and pumps over here. Again, be careful with the kinetic energy element in here. You may have to add that in here, the kinetic energy changes, if they're not negligible. But usually potential energy changes are definitely negligible, so you could neglect that. Again, one simplified version of this would be if there's no heat transfer taking place, then you could neglect this term. But usually, as you will see in example 4.5, this term is not being neglected in this example. So it depends on what kind of problem you're looking at. So go ahead and solve this example 4.5. and see how you can apply these equations for a compressor. And yeah, so just go through that problem. You also have to include the ideal gas model for that particular problem over there. So definitely work it out yourself. Again, try and represent it onto a TV diagram so you have an idea how a compressor functions from a lower pressure to a higher pressure or a higher pressure to a lower pressure. Just go ahead and try doing that yourself as well. Also, uh, look at example 4.6 as well. That is also related to compressors and pumps. So just go through those two examples. And the next component that we're going to look at now, or the next device that we're going to look at, you could pause this video here, just go and work out the problems, come back to this video later, and then go ahead and look at the other devices that we're going to look at. So if you want to pause it, you can pause it right now. If you're not pausing it, I'm going to keep on going now and introduce the next device, heat exchangers. And these are devices that again exist all around you, and the purpose of these devices is basically to transfer uh, basically heat between fluids at different temperatures. And there's different ways to do it, there's different devices to do it. I'm just going to introduce those devices here, but we're not going to go into the details of it. What you will see is that this is this is called a direct contact heat exchanger, and we've got, what the thing to notice is that previously we've had only one inlet and one outlet, whereas now we've got two inlets and one outlet. So you've got a stream of fluid coming in here, a stream of fluid that is coming in here. Maybe this is at a higher temperature and this is at a lower temperature, and you want to increase the temperature of this fluid. So that could be one, and then you have this outlet over here where you have this fluid at an increased temperature leaving the heat exchanger. Two inlet, one outlet system. The other type of heat exchanger is, this is called a counterflow heat exchanger. And why is it called a counterflow heat exchanger? Because what you will see is that one of the fluids is entering from this side, and then it's going, basically it's traveling in this direction, whereas the other fluid is entering from this side within the tube, and it's traveling in the opposite direction. So basically there's a counterflow that is being generated. That's the only reason it's called a counterflow heat exchanger. So you've got two inlets and two outlets now. So do you see the changes that are taking place? Again, we're operating in steady state, but we've got more number of inlets and more number of outlets now. And a third type of heat exchanger, this is called a parallel flow heat exchanger. And why is it parallel flow? Because again, we've got two different fluids in here, right? So we've got one fluid 1, that is entering into the pipe and moving in this direction, and we've got fluid number 2, which is entering from here and is traveling in a parallel direction to the tube. So that's why it's called a parallel flow heat exchanger. Again, I'm not going to go into further details of it. There's so many different types of heat exchangers that you could look at, so many different configurations depending on your application of it. You've got these counterflow and parallel flow heat exchangers. Then you've got other types of heat exchangers like cross-flow heat exchangers. You've got automobile radiators as well. Those are types of heat exchangers too. So depending on the application, you look at different kinds of heat exchangers. And now, basically, because there's multiple inlets and multiple outlets, so that's why we can't reduce this into M.1 and M.2 anymore. You've got to look at the conservation of mass in terms of this equation, and the energy equation in this form. Okay. So, for example, I'll just give you an example for this kind of heat exchanger now. Because you've got two inlets and one outlet, what you will have is that you will have m dot 1, let's say m dot 1 is over here, and you've got m dot 2 over here. Let's say you call this m dot 3. So what the conservation of energy principle at steady state tells you is that m dot 1 plus m dot 2 is going to be equal to m dot 3. And now you could like plug that in here as well and go with this. So for a heat exchanger, again, the work interaction that is taking place is only the flow work. So you could usually neglect this term out of here. And what else? You've got heat transfer rate. Again, that is something that is dependent on the application that you're looking at. If the application is such that heat transfer rate is something that is not negligible, then you have to include that term here. Otherwise, you don't have to do that. Usually, the kinetic and potential energies of the streams of fluid that are incoming and outgoing can be neglected. So you can neglect these terms in here. And what you're essentially left with is this equation. And so you could work out enthalpies at the inlets or the outlets, or you could work out the mass flow rates at the inlets or the outlets, or you could work out the areas of the inlets or the outlets. So all you need is just this equation, and you could work out so many different kinds of variables. Yeah, so this is what heat exchangers are about. You have to go and look at different examples for it. Go through example 4.8 and 4.7, 4.7 and 4.8 in Shapiro's book. Try solving them yourself, and just so you have an idea of how heat exchangers are going to be working for you. And then one more device that we're going to look at is called a throttling device. And basically, throttling itself, what it means is that you're plugging in the device, or you're reducing the pressure in here by introducing a restriction. So you could have a valve in here, so you could screw this valve in here and basically reduce the pressure by reducing the flow over here. Or you could have something called a porous plug that basically reduces the pressure in here off the flowing fluid. Again, it's treated as a control volume, and because you've got only one inlet, one outlet, so m dot 1 is going to be equal to m dot 2, and the conservation of energy principle, then you could apply that in here. And usually, because obviously there's no rotating shafts in here, nothing like that, so this term goes out. And what you're left with is these other terms. You have to look at this term as well, because there's usually no significant heat transfers with the surroundings. So you could neglect this term as well. From the inlet to the outlet, potential energy changes are negligible as well. And what you're left with is this equation in terms of enthalpies and the kinetic energy changes. And now, although velocities can be higher or lower in here, but upstream and downstream of the flow, of the reduced flow over here, usually in most cases what we see is that the change in the kinetic energy of the gas or the liquid, whatever is flowing here, can be neglected. So if this term goes out, then essentially what we're left with is this equation, H2 is equal to H1. And for this Y, pressure at 2 is less than pressure at 1, you would have to go and look at example 4.9. And from there, this will be more clear for you. Again, you're looking at Shapiro's book. Just go and look at the throttling devices as well. When you have this idealization, this is an idealization, so it's not, obviously, there's some kind of changes in kinetic energy that are taking place. So you're idealizing this. But this idealization is important, especially when we're considering refrigeration systems or we're considering air conditioning systems. So this is something that you will be looking at when you are dealing with air conditioning systems or refrigeration systems in more detail. And now, because we've looked at so many different devices, 5 different types of devices, then usually all these components are not working separately. You could combine all of these together because obviously by combining these systems together, you could reduce the cost. You could um, maybe have an application where it would be beneficial for you to do that. And one of the ways to do that is um, basically what power plants do. So we're just going to look at that system integration over here, and this is essentially what power plants do. So you've got a turbine as one subcomponent in here, then the boiler and the condenser here are basically types of heat exchangers. So you've got one heat exchanger over here. Heat exchanger is represented by the symbol HX. So you've got 2 heat exchangers in here, 1 turbine in here, and 1 pump over here. And essentially, this is your entire thermodynamic system. And through this system, you could generate electricity. Because if you combine this turbine, which is producing mechanical work here, shaft work, you combine it with the electrical system, this would give you um, basically electricity. So go ahead and look at example problem 4-10 and just work that one out from Shapiro's book, and you will be able to see how basically if you've looked at this entire video and you looked at all the example problems, you should have a good handle on how you can work out problems that are related to devices that are operating at steady state. And that is what we're looking at when we're covering these 3 videos, that we're essentially looking at devices that are only operating at steady state.